Hello, class. This is going to be the Intro to Stats lecture for March 9th. Today, we'll go through sections 9.2 and 9.3 from the textbook. 9.2 is about linear regression. So last time, we talked about how to measure the strength of linear relationship between two variables, x and y. If linear correlation coefficient R is high or close to 1 or maybe -1, then the data shows that they're well approximated by a linear function. Today we'll talk about how to find the formula for the linear function approximating a relationship. Okay, so let's talk about the notation first. When we talk about the points x and y, x and y are actual data points collected. So maybe a point here is maybe x3, y3, the third observation in the data set maybe. But if we're approximating that y value for a given x, what we're going to use for the y value that's an approximation for y is going to be the notation y hat. So that's what I'm going to use to distinguish between the actual value of y that's observed and the value that we're approximating. For the formula for the line, we're going to use the form mx plus b, where m is the slope of the line, that's the rise over run. Or how steep that line is. And b is the y-intercept. That's if you follow along the line to the y-axis, that's where it crosses the y-axis. Okay, so hopefully this is familiar to you. Let's do a small example. Okay, suppose we're using a rideshare service like a Lyft or something, and it has some base charge of $4 just to use the service. And it also charges you 15 cents per minute, right? So if you have this type of relationship, 4 would be the y-intercept. That's the amount it's going to cost, no matter how far the car ride is. And for each additional minute, so if x measures the time that you use the rideshare service for, then the slope will describe the additional cost incurred when you ride the service for 1 minute more. Okay, so if we have a relationship like this and we want to compute the cost for a 12-minute drive, we will plug in 12 into the formula 4, and we get $5.8. Instead, if we have how much money you spent, $6 for 25 cents. And we want to know how long the drive was. We could solve for how long the drive was by trying to solve for x. So subtract 4 from both sides. And dividing both sides by 0.15. I think that turns out to be exactly 15 minutes. Okay, so hopefully This is just fine. Okay, moving on. Okay, so let's use some toy data. So let's say I have 4 data points given by these values, and those I plotted on the scatter plot to the right. And let's say the blue and the purple line you see through the graph, these are given by 2 different formulas here. So the blue one is given by 1.25x plus 0.5, and the purple line is given by the formula 1.5x minus 0.25. Let's say we want to compare which is a better approximation of the data set that's given. So here's how I'm going to compute it. Okay. I know it looks like a lot, but we won't usually have to do this by hand. This is just to illustrate how to compare better approximation of lines. Okay, so let's look at the blue line first. So here are the x and y values. And what we do here now is next compute the approximate value for y given an x. So if you take this x value 1 and plug it into the x in the formula, so 1.25 times 1 plus 0.05, we get 1.75. So that's the approximate value for y. If we go down the list and plug in different x values for the x in the formula, these are the numbers we get. The next column, D, this is what's called the residuals. So that is the error. So the actual y value minus the approximate y value. So here the actual y value in the first row is 1. The approximate value was 1.75. So 1 minus 1.75 is negative 0.75. So this is how off your approximation was. We can go down the list and compute the other 3 residual as well. Now, if this was a good approximation for the data set, then you want this residual to be small. Small and both close to 0 is what I mean, right? I don't want it to be big positive or negative number, right? So I want to give a measurement or like a penalty for being off, right? If I just kind of add up the residuals, negative residuals will cancel out with the positive residuals. So that's not a good measure for how bad approximation was. So instead, what we could do is look at the square residuals. When we square a number, then no matter what it was, negative or positive, it'll spit out a positive number. So if these are the squared residuals, we can add them up to see the total of how bad the approximation was. So this is the sum of the 4 squared residuals, 1.8750. By itself, it doesn't really mean much, but we can kind of compare against the purple formula over here. So we have a different approximation for the data set, and I've computed the same things. I computed the approximate y value using this new formula, compute the residual, and then I've squared the residual and added it all up. So that turned out to be 1.25. So 1.25 is less than the 1.8750. Uh, the residuals are smaller overall. Um, that's what this is saying. So if we were just comparing these two linear formulas, then purple is a better approximation than the blue one. So that's what this is saying. So this is what we're going to use for measurement of uh, how good the approximation is. So let me put it in more clear terms. Okay. So this is called the least squares criterion. A regression line, also called the line of best fit, is the line for which the sum of the squared residuals, that's what we computed, so is at minimum. So it's the smallest it could possibly be out of all possible lines you can think of. So again, DI, that's the residual, is the actual measurement minus the approximated value. Okay. So if you see this criterion, you might wonder, well, why aren't we using absolute value instead, right? Why are we using squares? So I have two answers for that. So number one is that it's calculus friendly. So calculus is not a required prerequisite for this course, but the calculus doesn't work well with the absolute value symbols. So we have one less tools to work with. And there's a little bit more serious problem in this case. That is that the regression line will not be unique. There's actually many choices that gives the smallest possible the sum of absolute value residuals. So it is actually kind of nice feature to have if different people computed the best line of fit and they came up with the same formula, right? So it doesn't depend on the person of how they picked their line, right? So that's why squared is preferred than absolute value. Okay, so I want to get to the formula for the regression line, but before I get there, let me introduce some notation. So if I say capital S XX, then we're talking about the sum of the xi values minus its mean squared. Okay. Notice that this is very close to the formula for the variance of the variable x, right? So if I take this and divide by n minus 1, this would be the sample variance of the data set. SXY looks like a similar formula. Instead of multiplying xi minus x bar twice, one of the factors is xi minus x bar, but you're going to multiply that with the corresponding thing for the y variable, yi minus y bar, the actual y value minus the sample mean of y. That's your SXY. You might notice that this was the numerator for the linear correlation coefficient R. Okay, and we're using both x and y here, so this is called SXY. Maybe you can kind of see the naming notation here, convention. And we have a similar thing for SYY, so we multiply yi minus y bar twice and add those up. That's your SYY. So that's that. Okay. So once this notation is set, we can compute the slope of the best fit line is going to be SXY divided by SXX. And once you have that slope, the y-intercept is y bar minus the m that we just computed right there times x bar. So that's the y-intercept of the best fit line. It just looks like a magic. I just brought this out of nowhere, but you could get this formula using calculus. So calculus is a good tool when you're trying to look for maximum or minimum of something. And this type of like a least squares criterion where we're trying to minimize a particular thing, trying to find the minimum of squared residuals, and calculus is a good fit for that. Okay, so this is the formula over here. All right, so this is a beast to compute by hand. So the expectation is that you have a calculator to do this for you. So I've written out the restriction in TI-36X Pro. That's the recommended calculator for this class, and TI-8X, so maybe 83, 84, 85, these type of graphing calculators. Okay, let's see if I can fit the whole instruction. Okay. Okay, so please pause in 3, 2, 1 now, and see if you can compute the linear regression line for the data set that's given to us. The data set x, y, 1, 1, 2, 4, 1, 2, 2, 6. Okay. If you're using a graphing calculator, TI-80 something, it is possible that you could get just the formula for the line, but you might be missing the linear correlation coefficient or the R squared. If you're missing those two, then please follow this instruction right here. So you have to set your calculator so that the diagnostic mode is on. And you can get to the command by pushing second and catalog. I think that's the 0 button. And then scroll, it's in alphabetical order, so scroll down to diagnostic on and then press enter twice. Once you do that, now when you compute linear regression in the future, so you only have to do this once, you don't have to do it again. When you compute linear regression in the future, it will also give you the R and R squared, as well as the formula for the regression line. Okay. All right. So I want to talk a little bit about the R square that appeared in the calculator. So R square has a special meaning, and hopefully I can draw it right over here. So on the left here, I usually draw lots of cloud or points, but let's just work with the yi here, just 1 point out of maybe lots of points that we have. So let's say I'm trying to approximate this point yi. If I didn't know anything else about the situation, then just without knowing anything else, the best approximation for y is its y bar, its value, because I don't have anything else to go on. But if I'm given a regression line, let's say, then I have a better approximation of y value as long as the x value is given to us. So if I plug in xi into the formula for the regression line, I have a approximate value y hat. And my approximation just got better from y bar to a lot closer point on the line, but you're still a little bit off. So there's this different level of approximation of yi. So let's see. This distance from y bar to yi is variation explained by the line or the model. Right? Because if you didn't know anything, y bar is the best guess for y. But if you have x as well, then you have a better approximation. That's the part that's explained by the variable x. And the distance from the approximated value to the actual value, this is the variation that's unexplained by the model. So it might be that there's some other variables that you're not considering in the situation, or maybe it's just random chance. But this part was not captured by the relationship between x and y that we computed. So there's 3 different variations here. The total variation is the distance between the observed y value and y bar. So that's the distance from here to here. It's the total variation. The explained variation is from the line to the mean value. So that's the variation here. And the unexplained variation is the distance from the actually observed value to the approximated value. So that's this part. So it turns out that you can kind of break this variation up into these 3 pieces. And if you want to know what percentage of the variation is explained by the formula, you could just look at the ratio of the part that's explained by the formula divided by the total variation in the variable y. That happens to be what's called r squared, or the coefficient of determination. So r squared is literally a ratio. So it's going to be, well, it's going to be a positive number. So it's going to be between 0 and 1. And you could interpret this as the proportion of variation in the y variable that's explained by the regression model. Or when I say model, in this case, we mean the regression line. So if we look at an example, let's just kind of scroll back. Okay. in our last toy example, we got the r squared of 0.9152. That is saying that this formula explains 91% of the variation in y just by looking at x. So x's explaining power of y is very strong. It explains more than 90% of what's happening with the y. That is what that number is saying. Okay. And it also happens to be the square of the linear correlation coefficient r. So you might be wondering why coefficient of determination had was denoted r squared. That's because it is related to the linear correlation coefficient r. That's what we did in section 9.1. So they are related. But I use this language here. It happens to be a square. I use a language like that because it seems like it's more of a coincidence rather than some deep mathematical connection between the two different constants that were presented here. There's definitely a connection. I'm not trying to say there isn't, but this only works when you're working with linear relationship between two variables x and y. You could do this regression relationship with other shaped curve like exponential relationship or some kind of oscillating sinusoidal relationship, or maybe parabolic quadratic relationship, or maybe a relationship that involves more than one predictor variable. So I have to use more dimension than this to graph it, but you could do a regression with more than one predictor variables. In all of those cases, you could still define what's called coefficient of determination using this ratio of how much of the variation is explained using the equation that's given divided by the total variation in the response variable we're looking for. But in those instances, it's not a square of the linear correlation coefficient r. So in some sense, this is the only case when you have two variables x and y, and you are also looking at a linear relationship, not any other type of curves. So that's the only situation where this linear correlation coefficient and coefficient of determination is related by this square thing. Okay. So one more thing about the warning in trying to predict y value using this regression equation. When you approximate y values, it's good practice to only stick to the x values that's given within the original data set used to compute the regression equation. If you are plugging in x values outside of collected data, that is called extrapolation, and it is considered a bad practice. So for example, let's say I've collected these few different points that's given by maybe looking at the price of used car or something. So if maybe X is how old the car is and Y is the price that it's sold for. If you plug in an X value that's way high, like here, this regression line would predict it's a negative price, right? So somebody's giving you money to buy an old car, and that doesn't make sense in context. And that's because like these relationship between X and Y doesn't have to be a line forever, right? Maybe it looks like a line in a given data set, but maybe it changes the behavior after a while. So maybe it's more realistic for it to slow down if we collected more data. Right. So extrapolation is considered a bad thing to do unless you can back it up with maybe a theory or some other reason why the relationship should continue. So if you're just going by the data, then you should stick to X values that's given in the original data set. Okay. So the last example problem here, I want you to pause and try to see if you can predict, right? So if I give you this data set, it's a relationship between people's age and the amount of sleep they get in hours per day. Let's say I've collected data and I've got these 7 data points. Okay. What I want you to do is to pause this video and figure out what's the regression line between these two variables using your calculator. And once you get the relationship, I want you to predict the amount of sleep that a 25-year-old, a 50-year-old, or 16-year-old would get, as long as predicting it is a reasonable thing to do. So please pause the video and try it out for yourself. So 3, 2, 1, pause. Okay. All right, so if you've computed the regression line, what I got was something like this. I got y hat was equal to negative 0.0865 x plus 10.4495. I'm using a lot of digits here, but it is good practice to use more digits than you intend to use, and then round at the very end. So if I plug in 25 for x, I get 8.29 hours of sleep for 25-year-old. And if I plug in the same thing for 50-year-old, I got 6.12 hours. The 16-year-old is a trick question. If you look at the X values for the given data set, 16 years is outside of the range of the original set. In fact, the youngest person on this data set is 20 years old, which is older than 16. So this is an extrapolation. So it's not appropriate to predict the amount of sleep that 16-year-olds get given this data set. So if you wanted to predict the amount of sleep that 16-year-olds get, you need a bigger data set that considers subjects that are younger as well. And hopefully, if the linear relationship continues within the age range, then you can use that new formula. Or maybe it doesn't continue nicely as a linear relationship, in which case the coefficient of determination r squared might be a lower value. So the usefulness of using the formula for prediction might be little bit less, right? So that's it. That's it for chapter 9. Okay.